In this video, we're going to manage and display sprites from the arcade and demo sprite sets that are included with White Lightning. When we say the word sprite in White Lightning, we're actually talking about software sprites, not the hardware sprites that we're used to on the Commodore 64. But White Lightning does support hardware sprites, and we'll deal with that in a future video. By default, White Lightning can manage up to 6K of software sprites, and the limit can go even higher, up to 11K. Forth is a pretty unique language, and it's pretty different than I think any other language I programmed in, so I would highly recommend watching the previous 5 videos before this one. So a software sprite is a high-resolution bitmap that is divided into 8x8 blocks of pixels. Each pixel can have one of 2 different colors assigned to it. Each block can have its own individual pairs of colors. This is a 4x2 sprite of a biplane, where the top 8x8 blocks have different color pairings than the bottom 8x8 blocks. The sprites can be as large as memory allows. There can be up to 255 sprite shapes loaded into memory, and they can all be of different sizes. These sprites are uniquely numbered 1 through 255, where sprite 0 is a quote-unquote magic sprite representing the entire screen. There's a ton of commands in its library for moving sprites to the screen, screen to the sprite to sprite, there's a lot going on. White Lightning includes also a comprehensive software sprite editor, and we will explore that product in a future video. But for now, we're going to work with the demo sprites that come with the system. To load the sprite sets into memory, we need to learn a couple of new things about Forth first. Let's talk about numbers for a moment. When you type something into Forth, the interpreter needs to decide first if what you typed in is a word or a number. So if I were to type in, for example, some gibberish and press enter, you get this error 0, which means it can't find the word in a dictionary. And of course, the dictionary can be viewed by typing in vlist, and here's all the words in a dictionary. I just press run stop to stop the list from displaying. If you type in a number, what's happened is Forth has looked in the dictionary for 1, 2, 1, 3, 4. It couldn't find it. Then it looked at the block of text and tried to decide if it's a number. And it's a 16-bit number specifically, and it put it on the stack. Thus, you get the word OK. And in previous videos, we learned that the word dot will pull the number off the stack and display it on the screen. This version of Forth treats all numbers as 16-bit values. And then when we display it, they can be negative or positive. So for example, if we display 32,767, the number is correctly displayed as a positive number. What happens when I try to print 32,768? You get a negative in front of it. And this is because bit 15 has a 1, and that signals that this is a negative number. So here, when you're displaying positive negative numbers, the value ranges from negative 32,768 to positive 32,767. If we wanted to see what this number looked like as a unsigned value, we're going to use a new word called u dot, unsigned dot. And here it'll display the value, 32,768, instead of a negative number. When dealing with memory addresses, as we are in just a few moments, we really want to deal with just positive numbers between 0 and 65535, which of course is the addressable memory of an 8-bit computer. Memory addresses are generally easier to read and write as base 16 numbers, or hex. Forth luckily lets us switch between base 10 and base 16 really easily. So let's start with, for example, the hex number C000. That number should be 49,152 in decimal. If I press enter, it looks for it as a word, can't find it as a word. The number interpreter looks at it and it sees letters and it's like, well, that can't be a number, and thus we get the cannot find word in dictionary message. We can configure the number interpreter to go to base 16 by typing in the word hex. The word hex switches the number interpreter to base 16. So now when I type in C00, we get OK. And of course, we can do u dot to display it, and it gets echoed back to us. And just like base 10, there are negative numbers. So if I were to do C00 and try to display it, you'll get this negative 4,000. So again, when dealing with memory addresses, we want to use u dot. To switch back to base 10, we just type in the word decimal, and now we're in base 10 again. We can take these words and put them together, and then we can easily convert from hex to decimal. So for example, we could say, go to hex, put the number C00 in a stack, go back to decimal, and then display it. Pretty straightforward. The next thing we need to learn before we can start loading things into memory is how temporary strings work. Don't worry, this is a really short topic. There are some words that need the memory address of a string in order to process it. And one search word is recall, which is where we're going to learn in a moment, that loads sprites into memory. So let's start with what we're familiar with. When we type in dot quote space, that word is to display text, and we type in hello world, it actually behind the scenes creates a temporary string, reads it back, and then displays it. But some commands need to have that string just sitting in memory so it can look at it to do what it needs to do with it. For example, a file name that we're going to load from disk. So how do we create a temporary string? Well, use the word quote, you put a space, and then anything you type up until it sees another quote will be turned into a string, and it will be stored in memory, and that memory address will be placed onto the stack. So when I print this, it's going to say, okay, I'm going to type in the word hex because I want to see this memory address as hex, and we're going to use u dot to display it, and there it's sitting at memory address 4791. Now we can see that they give us a really cool command in White Lightning called dump. If we push an address onto the stack, 4791, and you use the word dump, it'll actually hex dump that section of memory to the screen. And here we can clearly see the word hello world at 4792 and forward. At 4791, there's a B. So the first byte actually tells the string how many characters it is, in this case 11, followed by the 11 characters of the word hello world. And now we have enough knowledge to load these sprites into memory. So if you look at this directory of White Lightning, you'll see that there are two files called demo1 and demo2. Demo1 is a file, it's about 6K, and it contains 59 arcade sprites. And these are like just typical sprites that you could use in creating some simple arcade games. Demo 2 is a little bit bigger, it's about 7.5K, and it contains 27 sprites that are used by its demo program. We'll show you that demo program later, it's actually quite neat. What we want to do is copy these two sets of sprites onto our source code disk. Now if you look at our source code disk here, you'll notice that there's 300 blocks free, and if you remember from, I think it's the second video, that half the disk was allocated because White Lightning stores its source code in raw sectors on a disk and leaves the other half of the disk as a normal disk for us to read and write files to. So we're going to put in the White Lightning disk into the disk drive, and we're going to load in the demo1 sprites into memory. And you do that with quote demo1. And again, this creates a temporary string with the word demo1 in it, and then we use the word recall. This is going to load those sprites into memory, and they will be available for us to use. But we do want to store a copy on our source code disk. All right, so we'll take this disk out. We're going to put our source code disk in, and we're going to do demo1 again. Again, it's going to create a temporary string. Except this time we're going to use the word store, and this is going to write the sprites that are in memory to disk. Great, now let's do the same thing with demo2. So we're going to type in demo2, recall, and before I press enter, we're going to switch the disk to the White Lightning disk, and then we're going to press enter. So what's happened now is my computer crashed, and there's a reason for that. By default, White Lightning lets you load 6K of sprites into memory. We just tried to load a 7.5K sprite file into memory, and that caused the computer to crash. You don't get an error message, it just crashes. So let's restart and explore how to solve that. Okay, so now that we're back on White Lightning, we need to configure White Lightning to be able to load more sprites into memory. We're using the disk version of White Lightning. There's also a tape cassette version of White Lightning. And on the tape version, it lets you keep 11 pages of source code in memory, and then you read and write all of them at once when you're done. This way you're not constantly, updating your tape cassette. So what happens is when Lightning starts up, it takes about 6 of those screens away and gives it to our sprite data. So if you look at this chart, we just want to move that bar all the way up because we don't need any of these screens because we're using a disk version. So what we want to do is we want to tell White Lightning you can use up to memory address 7800 for sprites. So what you type in is you type in hex to put us into hex mode. We're going to put the memory address 7800 in a stack. We're going to type in the word low mem. That sets the low memory marker, again, to give us more room for sprites. And then we'll switch our system back to decimal. And now we should be able to recall that demo2 file without any error. So we'll put demo2 as a string onto the stack, and we will use the recall word to load it into memory. All right, I'm going to put our source code disk in. And now we can call the store method, and now we have our own copy of the demo sprites to play with. Now, the only catch though is anytime we work with those demo sprites, we have to issue that command, that hex 7800 low mem command, before we can use them. We're going to forget that. So what we're going to do is we're going to look at our page of source code on the first screen, and we're going to add it here. This way, when we turn on our development system, we just type in one load, we get our initialization screen, and then here we're going to add a command to configure the memory for it. What we're going to do is we're going to insert a blank line at line 4, and we'll use the spread lines command. So 4 space S will insert a blank line at 4. Then we're going to place our code at line 4. I'm going to say hex 7800, low mem, go back to decimal mode. Then we flush our changes to disk. Definitely check some of the earlier videos where I show you how to use the screen editor. This editor, not the most user-friendly piece of software to use. And now we're going to review the source code on that screen, and there we are. So now going forward, when we boot up White Lightning, be sure to type in one space load, which will load the first page of source code and execute it. And here we go. Now we're ready to roll. Okay, let's just make sure that our demo 1 sprites are loaded by using the recall word to get them into memory. All right, I'm going to type in 15 window to split our screen to have graphics on top and text on the bottom. We're going to set the background to black, the foreground color to white. We don't need this third color because that's for multicolor mode. I'm going to call set ATR. And if you remember, set ATR sets the attribute that will be used going forward with sprite commands. We're going to set the sprite number to 0. And remember we said earlier that 0 represents the screen. And we're going to call sprite clear, SCLR. And now we have a blank screen. I think this yellow border is really, really ugly. So we're going to type in gray 2. And H border sets the color of the border when in high res mode. Oops, got to spell it correctly. So now let's draw sprite number 1 that's in memory to the screen. So the way that's done is we put a 1 in the SPN number variable, that's the sprite number, and then we're going to set where in the screen to store it. And remember, each one of these values is an 8x8 block. So we're going to display the sprite about 15 characters across and on the 8th row. All we need to do now is type in PUTBLK. This puts a sprite onto the screen using what's called the block method. The block method will copy the sprite to the screen, overriding anything that's in its way. And here we have a yellow ghost. Let's see what other sprites are here. So we're going to put a 2 in a variable sprite number, and we'll do a put block there. And here we have a little white guy. And if we try sprite 3, we have like a tank, and then we have 4 is like, that's the airplane. And let's see what 5 is. 5 is a helicopter. So there's a bunch of cool sprites there. So in order to really utilize the sprites, we really need a way to see all of them. There is a lot of sprites, and I wouldn't mind knowing what we have available to us. So we're actually going to write a utility program for ourselves that's going to create like a contact sheet of these sprites, so we can maybe print them out and put them aside so it's easy for us to reference. So I wrote a little program that does that. We're going to clear out the 20th page of code. I'll use 20 space clear to do that. I'm actually going to jump into low res mode here. This way we don't get all the screen flickering when we're doing things. And I'm going to copy and paste this code into our page 20, and then I'll explain what it does in a moment. So don't worry, this is not me typing really fast. I'm just pasting it into the emulator from my little notepad on the side here. So we're going to type in 20 space load to load this code in, and it's going to compile a word called sprite sheet that's going to display all the sprites on our screen. And just a reminder that all of this code is available on the GitHub page linked in the video. What this program is going to do is it's going to clear the screen, and it's going to place the first 30 sprites it finds in memory onto the screen. So we'll just type in sprite sheet, and there's the first set of sprites. 5, 10, 15, 20, 25, 30. 30 sprites. You can clearly see here that each sprite has its own bitmap data and associated color attribute data. And if you press enter, it's going to bring you back to low res mode. So if we type in sprite sheet again, it'll print the next set of them, and here it prints another 20. If you remember earlier on in this video, I said that there were 59 sprites in the first set, yet we only see 50. Each sprite in memory has a number associated between 1 and 255. You don't have to actually put all the sprites in order. You can put them in any order you want. And the arcade sprites clearly have sprites 1 through 50, and there are 9 sprites that are numbers greater than 51. We don't see them because our sprite sheet program loops sequentially through each number until it doesn't find a sprite to display. Well, we want to kind of compress all the sprites together so we can see them all. So if I press enter here and I run sprite sheet again, there's nothing left and doesn't show anything. There's a word called Reseq, which is short for resequence, and what it does is it goes through each sprite in memory and assigns it a new number starting at 1 up to where it ends. All right. The sprite sheet program that I wrote works off a variable called sprite num. So in order for us to run it again, we have to reset it to 0. So we're going to type in 0, sprite num store, and now we're ready to run it again. So this time, the first time, we'll see the same 30 sprites we saw before. And then when we run it the second time, we will see that there's 9 new sprites at the bottom, and they seem to be 9 frames of animation of a man jumping. And that's going to be fun to play with in a few minutes. All right. Before we continue, I do want to save this new copy of Demo 1 to disk because it's really nice having them in order. So if I type in quote space Demo 1 quote store, that should save it to disk. You'll see that it has a disk error, and the disk error is the file exists. So to override it, we can use @:, which is a standard 1541 DOS command, before the file name, and then we'll just type in store, and this will overwrite the existing file. And now we will have a copy of Demo 1 where all the sprites are in sequential order, so it'll be very easy for us to reference in some future projects. Now that we have the source code on page 20 that's really useful, let's update the code on our page 1 to point ourselves to that code in the future, because we're going to forget that it's there. So what we're going to do is we're going to put a comment on line 8. So we'll do 8p, and we're going to say on page 20 is the sprite sheet program. All right, and then we'll flush the disk buffer back so it's written to disk. I'm going to show you now how next to run this program except by having a white background and the sprites appear in black. This way we can use it to print out like a little lookup sheet for ourselves to use so we can pick sprites in our future projects. So let's first reset the sprite num so we can run our program again. We're going to say white background, black foreground. We're going to set that as an attribute. Okay. We're going to set 0 as a sprite number, which again is a screen, and we're going to clear the screen. We're going to do a command called att_off. What att_off does is it says that when we use commands like put block to copy the sprite to the screen, don't bring over its color data from the sprite, use what's already there. This will give us a printable page. So let's see how this looks. Perfect. So I'm going to grab a copy of this, and I'm going to put it aside. And then we're going to run it again to get the second part of it. I'm going to grab this and I'm going to put this aside. So we added these 2 images with the sprite numbers under them in GitHub, so you can take a look at it and use them yourself. Okay, so now let's take a few minutes and let's talk about how this sprite sheet program actually works. So the first thing this program does is it declares a variable called sprite num, and that number is increased by 1 as we place sprites onto the screen. The code between 1 and 11 creates a new word called sprite sheet. And the first thing it does is it sets the background to black, the foreground to white, the third color to 0 because it's not needed since we're not using multicolor graphics mode. Set ATR takes those values and sets the attribute, and then high res switches us into a full screen high res screen. The next thing we do is we set the sprite number to 0, which is the screen, and we call sprite clear. Now here's where the real meat of it works. We create a loop that runs from 0 to 6. Now loops in fourth are not inclusive of the last number, meaning 0 through 6 actually runs 0 through 5. Thus we get 6 rows on the screen. So the way the do loop works is it takes the 0 and the 6 off the stack and it starts looping through it. The letter I is a fourth word that takes the iteration and throws it onto the stack so we can use it. So in the first iteration of the loop, it puts a 0 onto the stack. We're going to multiply it by 4 so we can move down 4 blocks for every row. So 0 times 4 is the top row, 1 times 4 is the second row, and so on. So we put the 0 on a stack, the 4 on a stack, we call star to multiply it. That leaves the value on a stack that we want to store in a row variable. Now we have an inner loop that does the same kind of thing except for the columns going across. So this do loop will go to 0 to 5 minus 1, which is 4, so 0 through 4. Now we take a 1, we put it onto the stack, and we call sprite num. And here's a new word we have not seen before, which is plus store. The way plus store works is it takes the number that's on a stack, which is 1, adds it to the value that's already in sprite num, and stores that into the value. So basically, it increases the sprite num by that number on the stack. Line 8 takes sprite num, it fetches it out of the variable, puts it onto the stack, and then we store it into SPN. So it sets the sprite number that White Lightning is going to use. Then we take I, which puts the iteration of the do loop onto the stack, so it's going to be a 0 at first, and we're going to multiply it by 8. This is how we position each sprite being 8 columns across. So we take that multiplication by 8 and we store it in the col variable. Next is a new word. It's called DFA. There's really no great acronym for it. What this does, it takes the value in SPN, looks up the memory address of that sprite data, and puts it on a stack. If there's no sprite data, it returns a -1. Now here's another new concept we have not run into before: comparing values and making a decision on what to do with them. In this case, DFA puts a memory address on a stack. We're going to put a -1 on a stack, and the word equal will tell us if they're the same or not. If they're the same, it puts what's called a true flag on the stack. If they're not the same, it puts a false flag on the stack. Now that the stack has a true or false flag on it, we can use the word if. The way if works is, if there's a false flag on the stack, it will run the code between else and end if. If there's a true flag on a stack, it runs the code between if and else. So ultimately what this line does is, if there's a sprite to display, we call put block. If there's not, we don't do anything and we loop to the next position. Those two loop words, of course, enclose our loops. So now on line 11, when all the loops have run, it runs the word key. And what key does is it waits for a key to be pressed on the keyboard. When you press a key on a keyboard, it returns the value of the key onto the stack. We don't really care about the value, so we use the word drop. Drop takes the value in the stack and just tosses it. And then low res switches us back to low res mode. And that is how that code works. Okay, now let's have some fun. We're going to animate that man that had all those frames of animation at the end of our second contact sheet. All right, so if you look at our sprite contact sheet, you'll see that we want to animate sprites 51 through 59. And we want to do it in two directions. We want to animate going forward where he crouches down, and then we want to animate backwards where he crouches back up. And we can do this with just two simple for loops. So here's how it's going to work. All right, first we're going to clear our screen back out. So we're going to turn attributes back on. Sprite 0, white background, black graphics, set the attribute, then do a sprite clear. We'll jump into 15 window mode. Oop, there's that ugly border again. So we're going to do a gray 3H border. And ooh, maybe gray 2 might be better. How about gray 1? There we go. All right. And we're going to create a word called animation, or anim. So we're going to turn attributes off because we want to copy the sprite to our screen using our black and white colors that we already have here. We're going to do 15th column and the 8th row, so we'll store those variables here. And then we're going to start our first loop. We're going to go from 51 to 60. We're going to create a loop here. We're going to throw I into the stack, and we're going to store that in a sprite number. And then we're going to call put block to put the sprite on the screen. Then we're going to take a short break for about 500 iterations, and we're just going to do an empty loop to kill some time. All right, and then we'll end this loop. Now it gets interesting. We're going to do the same thing, except we can go backwards. We're going to go from 59 down to 51. And once again, you never actually get to the 50, so this will end at 51. We're going to take the loop iteration, throw it on the stack, and store it in sprite number, and again, do a put block to put it on the screen. All right. Then we'll do another little 500 loop there to kind of break some time there. And now instead of doing loop, because we want to count backwards, what we do is we put -1 on a stack, and we say plus loop, meaning loop and then use the value that's on a stack as the step for it. And then we'll just end the word. So now in theory, we have a word that'll animate a man going down and coming back up. So let's give it a shot. And there it is, pretty cool. And of course, if we wanted to see it animated quite a bit, we could just run it over and over and over and over again to kind of get a little bit of an animation there. That's pretty neat. So of course we can make another quick word to have this thing animate quite a bit. We'll do a, I don't know, 2000 do loop, and we're going to call it our animation word. All right, we'll let this run. I put the source code for the anim word on page 21 of the disk that you'll find on GitHub in case you want to play around with it. So we covered quite a bit of ground in this video. We got sprites on the screen, we created a contact sheet, we explored do loops, we explored how to test variables, and we did some animations here. So my goal in the next video is to cover how to write code using interrupts in Forth, and it's going to be really neat. We're going to animate an entire scene and hopefully make it look pretty cool. I would really like to say thanks to all the people that left such nice comments on these videos. I also want to thank you for the super kind words and emails I received over the last few weeks. Thank you guys so much. I'm really looking forward to getting more content out. And now that I have some more time, I should get some really cool stuff out. Again, thank you everyone for watching and being so supportive of this. Thank you.